Good afternoon, everybody, and welcome to the presentation of my paper, which has the title Effect of the Traversing Unit on the Flow Structures Behind a Passenger Vehicle. I would like here also to mention that this paper has been written in collaboration also with my supervisors during my PhD project, which are also the co-authors of this paper. There are Professor Lennert Sterken from Chalmers University, and also Lennert Sterken and Tim Walker from Volvo Cars. I would like to say that this paper is actually a result of some kind of a spin-off from my own PhD research, in the sense that the original basis came from my very first wind tunnel test I conducted in the Volvo Cars aerodynamic wind tunnel. The test had actually to do with making wake measurements because I was interested in the wake flow behind the car. The wind tunnel engineer asked me if I wanted to also save the forces measured by the balance of the car as well, which at that moment wasn't done. So I was a bit surprised from the question because it was my first test. So a little bit unknowing, I said, yes, of course, I would like to. I'm interested in the balance forces as well while conducting these wake measurements. And that looking later, it showed that there were some variations in my balance forces as well. And this kicked off then also this paper. So first, as a content of this presentation, I would like to give still a small introduction. Then I would like to describe the methodology used, the setup, because this is mostly a numerical simulation paper, and also the configurations which were tested. Then I would like to continue with results, looking at the global forces, and also at the flow structures behind the vehicle as well. And I will sum up with some conclusions. So when like I said, when we make some wake investigations behind the car, we use a traversing unit consisting of where we attach two omnidirectional pressure probes to it as well, and we orientate it at a 45-degree angle. And then we have two methods to take these wake measurements. We have a step-by-step method where we go basically from point to point, and then we stay there for 2-3 seconds, and then we move to the next point, and in the meantime, over those 2 seconds, the pressures are averaged. And the second, more new method is a sweeping method where we sweep along one axis before going to the other axis and go backwards. And then we use some filtering technique to get the average pressures out of it as well. My research car is actually a Volvo XC60. So I have used this car as well in my numerical simulations node to investigate what the effect of the traversing unit is also in the numerics as well. So what I said at the start of my presentation is that when I originally looked at some of the force measurements measured by the balance in the wind tunnel, I could see some differences, and what I show here in this plane is the drag force measured by the balance, not by the pressure probes, but just by the balance when the traversing unit is in a specific location of the plane, and I compare it to actually the drag force or the drag coefficient when the traversing unit is in the parking position, like 50 meters away outside of the test section, and then I compare these two values. On the left side, I show you a transverse plane around, which is typical at the Volvo is to do at 100 millimeters or behind the vehicle, and then you can see that on the right side here, when the traversing unit is still in the free stream flow, that you have like a difference of 5 dracons. So it's not insignificant because the wind tunnel during one test has an uncertainty of only 1 dracon. So there is definitely some difference. And if you take a constant height plane, the right plane, which is here around the top of the wheel arches at 750 millimeters above the ground, then you can actually see that when the traversing unit is moving away from the car backwards, that the CD value measured by the balance is actually lowering also with 5 drag counts again. So that was quite significant. So we thought about it to investigate this using CFD. For one reason, it would actually give us then a better understanding of how our wind tunnel was working, and we could also correlate it then further with some other research projects we are conducting at Vovekars, which is more related to the research of our full-scale wind tunnel. So this would then help in that understanding. So first thing we had to do, because we didn't have a CAD model, was actually scan the traversing unit in the different sections. So it consists of a general box-like shape, which is around 5 meters long from nose to trailing edge. And on top it has like these two wing-shaped profiles over which the top box can actually basically slide to go to the different positions. And then you have like also an arm or a sting, to which then at the bottom the pressure probes are attached under a 45-degree angle. Later on, I will make a difference between the effect coming from these wings and the sting as well in the further analysis in my results description. So what I did during my numerical simulations, I used simply the steady state runs simulations with a realizable K-epsilon turbines model, simply because it's actually our default procedure and it's relatively fast to investigate if there are any flow structures difference. And I used 2 wind tunnel approaches. The first one was a simplified box-like wind tunnel, where I replaced the Volvo XC60, but behind it the traversing unit scanned in. And as an initial test, also we tried to implement it into the PVT wind tunnel on the right. The PVT wind tunnel normally has slotted walls as well, which I have now removed for a better just visualization, so that you can better see the car with the traversing unit positions. If we look at some of the configurations which were investigated, I wanted to stay close to the same wake planes as I took during my experimental results. So I took 2 transverse planes. The first one is the one 100 millimeters behind the car, where I took 5 points, basically spread out over the complete area of 1, 2, 3, 4, and 5, over the complete area of the plane. And the second one, 6, 7, and 8, was 750 millimeters behind the car, so a little bit more further away. And then also I took the ones close to the ground, and one like to match with the top of the wheel arch again, just to match my other experiments. So if you look at the results and we start with the global forces from the simulations we conducted in the simplified wind tunnel, we can actually split them in 3 parts. The first part is when we take the transverse plane 100 millimeters behind the car and we stay close to the ground. Then we saw actually quite a big drag increase coming from the traversing units, while also it had effect on the front lift and also on the rear lift with almost more than with a decrease of 15 lift counts in the rear as well. A second division which can be made is maybe like the 100 millimeter plane, but when measuring closer to the roof of the car, then you still had an increase of drag, but a little bit less significant than before. Not so much a frontal lift, and still we had a rear lift change as well, with a decrease. Going further away from the car to 750 millimeters, then we started to see that these effects were starting to reduce to much lower values as well. So if we then start to look at if there are any flow structure differences coming from the traversing units, Then I'll split my results into a traversing wing effect, and later on comes the sting as well. But first we start with the wing. Then I have on the left side the reference, which has absolutely no traversing unit. So traversing unit is not present. And on the right side we have the traversing unit with at the lower left position of the car. And what you can see is actually that if you look at you can see like an increased velocity which is connecting with the shear layer coming from the first wing of the traversing units. And that has a consequence as well further downstream as well, where you can see the slide it doesn't go down as much as with the reference, so you get like a wake lift in a sense. If we look at this from a different perspective, then we plot local drag, which is just a visualization of the contribution of local drag in the fluid flow, and it's superimposed here with total pressure contours. Then we can see, of course, that the wing itself generates a small wake, but also when we mention the force field, it's like the energy recovery is not as fast further downstream coming from the roof. And you also see from the ground, for instance, that you have a higher energy region much closer to the ground, which stays longer downstream. So you get also a small lift of the wake. If we move to the traversing arm or the sting of the traversing unit, and we compare again between the reference, having the traversing unit on the lower left side of the car, you can see it here with the white, which is the white traversing arm, and here on the lower right section. So here it's in the free stream. Then you can see that with the traversing unit at the lower left position, that it has actually interference with the ring vortex generation on that side, and that you have a much more of an inwash of the flow on that side compared to the reference. If we then compare this to the traversing unit on the lower right side, then you have again a velocity interference between the traversing arm and the shear layer on that side, causing at that side again a stronger inwash of the fluid flow into the wake. Here we can actually also look at from a local drag perspective, and then you can see then as well that from the traversing unit on the lower left side, you have this interference where the shear layer wants to go to both sides of the traversing arm, and you get a better pressure energy recovery on that side. On the right side, you can see that the energy recovery is better on that side compared to the reference. If we would now compare this, like I've said in my methodology, to the simulations conducted at the PVT full-scale wind tunnel, which I also conducted, then it shows very similar behavior. However, I only took like 2 simulations to confirm this, and they showed the same, but I didn't do for all configurations in that wind tunnel. Simply because it just this was just more as a tool for further analysis in the future in other projects. But another question which can be asked as well is, okay, if we see changes in the wake as well, can we see changes on the surface pressure too? And that's what we see in this slide, is where I plot the base pressure of the reference, and with the TU on the lower left, and here the TU on the lower right section. And then you can see that for one, you get actually, I hope it's clear, I try to make it visible with the contour lines as well, is that you get a lower pressure on the windscreen compared to the reference, as well as because you get a stronger inwash of the flow on the side of the traversing unit, the high pressure region actually moves to the opposite side of the traversing unit, and which is quite clearly visible as well. Simultaneously, as visible as the lower regions on the sides of the traversing unit, basically as well on the rear bumper height. So clearly, it is also traceable on the base pressures as well. If we then come to the conclusion, and maybe that could correlate as well to what was mentioned in the first presentation this morning as well, is if we want to correlate wind tunnel results and results from CFD as well, we should also, of course, take into account that when we measure the wake flow in the wind tunnel, that the device what we're measuring with has actually an effect on the flow what we want to know as well. So we should actually take that into account. We can't just ignore it and just say we just compare CFD directly with the wind tunnel results, because if we have a device, and definitely if the device is intrusive as the pressure as with the pressure probes and traversing arm, then we have to take that into account. So the simulations can confirm the wind tunnel balance measurements, so that there is a difference. And we see this effect from the wing by an increased velocity, for instance, on the roof shear layer, and it lifts the wake up. And also in the arm as well, because it inserts, the arm inserts an asymmetry in the wake flow, and has then an effect on the creation of the ring vortex behind the vehicle. And it should be traceable to, it's also traceable to the changes in the base pressure as well. And with that, I would like to thank you for your attention.